our last piece to this particle nature of electromagnetic radiation puzzle. All right, atomic spectra. So you may have remembered from your prep chem class this idea of atomic fingerprinting. Okay. Atomic fingerprinting. So we get these really interesting spectra where, we see these different spectral lines, and that helps us identify elements. All right, so our wave-like behavior didn't explain atomic spectra. So we get these gas discharge tubes, these cathode ray tubes, where depending on the element that I have in my tube, I get light. Okay? Now, some important things to understand. Not all wavelengths were produced. Only a few wavelengths or frequencies were produced. And different elements had different wavelengths. And we saw this in both the visible, or not just the visible, there's three, not just the visible spectra, but in the infrared and ultraviolet regions, okay? Now to get there, there were several experiments that were done to build this picture before we saw those nice, neat spectral lines, okay? So the first experiment was simply adding these different elemental gases into cathode ray tubes, okay? So different gases produced different colors. This is boring. Okay, this is what they looked like. All right, so we've got some helium, neon, argon, krypton, and xenon here. And you can see each one is unique. Each one produces its own unique color. All right, here's a few more. Hydrogen, deuterium, nitrogen, oxygen, mercury. Now, the only difference between the hydrogen and the deuterium is that the deuterium is all the isotope of hydrogen that has the neutron with it, because remember, when most hydrogen is just one proton, but there's a few isotopes of hydrogen that have one proton and one neutron, and a few even smaller that have one proton and two neutrons. Deuterated hydrogen is simply isolating just that isotope of hydrogen that has one proton and one neutron to it. All right, and so you can see the hydrogen and the deuterium, it's the same color, it's just the intensity is a little bit different. Okay, as deuterium's heavier. Okay, so they're all different. Every single element produces a different color. Okay, now, next experiment. I mentioned at the start of all of this that if you take a prism can separate out white light into individual colors. We get the rainbow. So if I have white light shining into a prism, all right, I get the full visible spectrum. Okay, so it looks like that. So our third experiment, what if we take one of those cathode ray tubes with an individual element in it, shine it through a prism, focus the light through a slit, and then see what gets produced? Because white light gives us all the colors, but my cathode ray tubes give me individual colors. So I shouldn't see the entire spectrum when I separate with the prism. And indeed, that's what happened, is we got distinct bands of color when we would shine it through, okay? So now the hydrogen spectrum for the longest time only showed 3 lines. As our detection has gotten better, we do actually detect a 4th line. So this is the hydrogen spectrum. So I've got the gas discharge tube up there in the left-hand top corner, and then the spectrum down below. And so you can see we've got more than 3 lines there. And so each element gave its own individual spectrum. And that's why we can call this atomic fingerprinting, because every single element is going to have its own unique spectra. And so one of the experiments that we do in our first semester general chemistry course at Grossmont College is we actually pull out these gas discharge tubes and the detection equipment, and the students get to go around the room and take a look at different elements. We used to identify all the elements. Now we do it as a mystery, and the students go around and they have to view the different spectra, take down in their lab notebook what they see, and then we give them a chart of possible different elements we could have shown them, and they have to compare what they saw to the known spectra of those elements and determine what elements were present in the classroom when they did the lab. Okay, and so that's what it looks like. You've got that gas discharge tube. It goes through a slit to focus the light, then the prism separates it into the individual wavelengths. And so every single element has its own unique spectra. Okay, and here at the top you can see a version of the hydrogen spectrum that shows all 4 lines. Now, as we're going to see as we go through more of this, is because hydrogen is such a simple system, hydrogen only has 1 electron. And it's much easier for us to track what's going on with hydrogen than any other element. As soon as we move to helium and we have 2 electrons, things get complicated. Now, it's not possible just by looking at the number of electrons or number of valence electrons or any of that stuff to figure out and predict exactly what line spectrum we're going to see. The only way we know these line spectra is by actually looking at them. All right? And so here's a few more. There's helium and lithium, sodium, mercury. All right, and so every element has its own unique spectra. And this is one of the ways that we can actually tell what elements are present like around a distant planet, is we do have telescopes and stuff that are up in orbit around Earth. And so and these telescopes can pull in that light from distant planets, focus it through, and we can get these spectra. And we can say, oh yeah, that planet that we have never sent a physical probe to has oxygen in its atmosphere or helium in its atmosphere. This is part of how we do that. All right, so now we've still got more of the story for quantum mechanics to tell, but this ends our story in what sorts of things we were observing that just didn't make sense if electromagnetic radiation was just a wave. And so now we've built that picture where we've got this wave-particle duality. Electromagnetic radiation does indeed behave as both a particle and a wave, which has interesting implications. Stay tuned.